So, welcome student to the next class of Introduction to Nonlinear Optics and its application. In the previous class we learned from the nonlinear Maxwell's equation how one can derive the equation for the second harmonic and fundamental wave, and how the amplitude of the second harmonic will going to evolve we figure out from the nonlinear Maxwell's equation. So, today we will going to use these two coupled equation that we have derived in the last class and try to solve it. So, solution is important, but we need to find out whether we can solve these things properly or not. So, today we have the topic, and the topic is theory of second harmonic generation, which we have already started in the previous class, that we are going to continue, and very important thing which is phase matching. What is the phase matching and what is the implication of second harmonic generation we are going to learn in this class. So far all the treatment is classical. So, I believe it will be easier for you to understand. One can also calculate these things, this susceptibility and other calculation in quantum mechanical way. For this particular course, we basically do not use any kind of quantum approach. So, classical approach will be our main emphasis, and I believe it will be useful for you also, because you need to understand the physics of this nonlinear optics, and classical treatment is easier for you to understand. So, okay, so let us try to find out the theory of nonlinear this second harmonic generation and the nonlinear optics, and how this theory basically developed. We already we have shown you in the previous class. So, today we will going to solve that two equations. So, let us go back to our previous slide. So, these slides already we have shown in our previous class that eventually we have two coupled equation, and these two coupled equation basically suggest how E1 and E2 will going to evolve. One interesting thing if you look, which is quite obvious, but still I will going to emphasize you to understand that what is going on. So, this is the evolution of the second harmonic. So, E2 is corresponds to the field which is containing the electric the frequency 2 omega. For example, this is the wave that is inside the material. Now, in the right hand side we have a source term. So, basically the source term suggests in order to excite the second harmonic you have some sort of source, and this source is nothing but the fundamental wave. So, fundamental wave basically pump, it is using as a pump that basically give rise to the wave which is having a frequency 2 omega. So, from here we have the energy, so that I will have some kind of electric field in 2 omega wave. Also we have another expression in our hand where we can see that we have the evolution of E1. That means, if this is my system, E1 will also going to evolve some way, and E2 is also going to evolve some way. We need to find out. So, this is over Z, this is E1 or E2, but from this coupled equation it is very difficult to say, because we need to solve this carefully, that how this E1 and E2 both are function of Z will going to evolve. But it is for sure that in order to evaluate E2 we need to make some kind of approximation, and in the next slide we will show what kind of approximation I am talking about. But here it is important to note that E2 will going to generate in presence of E1. That means, E1 is a basically some sort of driving force that generate E2. Also in the previous class it was a homework. I believe all of you have done this homework and you have this expression in your hand. So, with this confidence let us go to the next slide. Okay. So, our goal here is to, as I mentioned, our goal here is to find out the solution of this coupled equation. So, physically what is going on, let us understand. We have a E1 wave, this is the frequency of E1 and this is the frequency of E2, which is twice of the omega. If the frequency is omega, this is 2 omega, and we say that E1 is a strong pump. That means, we are launching some kind of strong E1, and try to find out whether because of the launching of this strong pump E2 will going to evolve or not, and this is the equation which basically guide us how E2 will going to evolve. Now, since E1 is a strong pump, I can consider E1 as a constant. So, that is a very important approximation here. So, this is not a very physical approximation for the time being, but this is not a physical approximation, but for the time being we can consider that E1 is a constant. For the strong pump we can consider E1 is a constant and try to find out what should be the value of E2 or what is the functional form of E2. So, now this differential equation is solvable because we have E2's dz and the entire term is now constant. If this entire term is constant, we can take it out from the integration. So, it is basically taken out. So, in the integration we have only the exponential term which contain this z, and integrate this both the side with respect to z, where we will do that for 0 to z. So, we integrate this differential equation. When we integrate this differential equation, we need to also consider about the boundary condition, and the boundary condition is that there is no E2 at the beginning. That is a quite justified approximation, because if this is my system and if I launch a strong pump E1 here, so E2 will 0 here, there will be no E2. Once the pulse is moving, the fundamental field is moving, what happened that it will basically feed the system, so that E2 will going to generate gradually. So, the boundary condition is E2 at z equal to 0 is 0. So, there is no E2 at z equal to 0 is 0. On the other hand, E2 at z equal to z is Ez, and this Ez basically we try to find out what value of E2 one can have at some z point. Okay. So, now the integration part, we know this integration, and this is a very straightforward integration. So, this will be E2 and this is a constant term, as I mentioned earlier, it will come outside, and this integration is e to the power I k z, e to the power I k z, and I k z will come, minus I k z will come here in the denominator with the limit 0 to 1. Once I put this limit 0 to 1, what we have is d I d omega into c multiplied by E1 square, and this boundary condition if I put, the first term will be to the power I delta k z minus 1, and the denominator will be as usual minus I delta k. We further simplify that and we will get something like, if I absorb this minus sign, so it will be 1 minus of this. So, I will have 1 minus of e to the power minus of I delta k z, so that we can absorb this minus sign. So, this minus sign was here, it was not here. So, it is plus. And finally, what we do, that this looks quite a similar term, or this is one can make some symmetric kind of term using that. So, in order to do that, what we do, that we multiply the entire stuff with e to the power minus of I delta k z by 2. When I multiply by 2, then one term we have here which should be e to the power plus I delta k z by 2. So, that when you multiply with e to the power minus I delta k z by 2, we will have 1 here, and since I am taking 1 e to the power I delta k z by 2 term, 1 e to the power I delta k z term will be still sitting here. So, we will have one term here and one term here with opposite sign, and delta k will be sitting here in the downstairs. So, with the I term. So, I think the I term is missed here somehow. So, it will be I delta k, here also we have some I delta k term with this in the numerator. Okay. So, after having this term, we can simplify and we will get some term which is some sort of, okay. So, here we have, okay, let me go back. So, let me go back to the previous term, so that we can understand. So, we integrate that, when we integrate we will have this, and basically, okay. So, this I will not be here, because one I was sitting here, I was forget about this I. So, this I and this I will be cancel out. So, one Once this I will be cancel out, there will be no I term here and also here there will be no I term. So, the expression whatever is written is correct. Okay. So, go back to the next slide. Yeah. So, we have one important term here there, which is e to the power of I delta k z by 2 minus e to the power of I delta k z by 2 with a negative sign divided by delta k. This term is nothing but e to the power of I theta minus e to the power of minus I theta. If I say delta k z divided by 2 is theta. So, once we have e to the power I theta minus e to the power of minus I theta, so we will have like cos theta plus I sin theta, one term. Second term is minus cos theta minus, or there is a 1 minus. So, it should be plus of I of sin theta. So, this cos theta term will cancel out. We will eventually have 2 I of sin theta, 2 I sin theta term. So, here we have 2 I, theta is in this notation, it is delta k z by, so we will have 2 of I of sin delta k z divided by 2 divided by delta k. That is a term that we have when we derive these things. Okay. We further simplify, since we have delta k divided by 2 and 2 term is sitting here. So, I will put this 2 term here, so that I have delta k divided by 2 here. In the numerator also I have in the argument of sine delta k z divided by 2. So, some sort of sinc function we have. So, this is the function which looks like this. So, this is important, you should correlate these things, sin x divided by x. We know this is called the sinc function. So, this is sometime it is written SINC of x, which is nothing but sine of x divided by x. So, sine of x divided by x term is something like this, but you should also note one thing, that one z is missing. So, if I multiply z here and multiply z outside, so we can write this as a sinc function, but right now it is not exactly the sinc function, because the argument here and this term is not same, but I can always do that by multiplying one z and in the numerator and one z in the denominator, that we will eventually do. So, after having E2, the next thing is that if I know what is my field, second harmonic field, which is E2, what should be the value of the intensity of that. So, intensity is nothing but mod square is a half of epsilon 0 into C mod square of the field. So, this expression we are using several times. So, you should remember the relationship. So, we know that I2, which is a function of z, is proportional to mod of E2 function of z square. So, once it is proportional to mod of this square, so we can readily find out what is the corresponding intensity. So, now this intensity can be represented in terms of power also by multiplying the area. So, if I do that, we will have the same expression multiplied by area. Since the value of E2 is known, I can try to find out what is the corresponding power. So, at the end of the day, we try to know that what is the second power of the second harmonic. So, that is why we can convert everything into power. Okay. So, if I do, so what value we are getting, let us find. So, E2 is this that we have already calculated, and we just put this value here. So, since it is a mod square, this I will going to absorb. So, there will be no I, and we will have some sort of sine of delta k z by 2 and then delta k by 2 whole square term, and this term is already there. So, we will have a square of that. So, intensity of 1, if I try to write in terms of intensity and power. So, the relationship between the power of the second harmonic and the first harmonic. So, E1 is sitting here. So, this E1 I can replace by I1, considering the fact that this E1 is a constant. Since this is a constant, we can say that it should not have any kind of phase. So, we consider this is a real. So, E1 is real. If it is real, so there is no phase term. So, E1 square is nothing but mod of E1 square. Since it is a real, that does not make any difference. So, I1 if I write, so P1 can be represented in this term. So, now if I put this E1 in terms of P1 here in this equation, we will have an expression like this. So, this expression is important, because in this expression we try to find out what is the power of the second harmonic, and in the right hand side we find that the power of second harmonic basically depends on few things. So, this is important. Physically you need to understand very carefully that what are the term for which this power is depending on. So, you will find that there at the term d sitting here. So, d is square, that means if the nonlinear coefficient is high, then P2 will be high, that is one thing. Second thing is that P1 is a pump and it depends on the square of the pump. So, if the pump is high, so there is a possibility that we have a very high second harmonic, the power of second harmonic. So, that is the term. Apart from that, one very important term is sitting here, which is sine square delta k z divided by 2 by delta k divided by 2 whole square. So, this is a sinc function, and we know that this function can reach to 1 when delta k tends to 0. So, we know that sine of x divided by x, if I make a limit x tends to 0, then this value is 1, and that is the maximum value. So, in order to maximize the right hand side, one very important condition is that delta k has to 0. This is basically called the phase matching. Phase matching. So, in the next slide we will be give you more information about the phase matching. So, let us go to the next slide. So, here that is the thing we try to emphasize, that we have a sinc function, we have a sinc function like the, we have a sinc function so we have a sinc function sine square delta k z divided by 2 and these things. So, in order to have this sin x by x form, we need to multiply 1 z, and after multiplying 1 z, if I make a limit, it will come as z square, as simple as that. So, P maxima, P2 maxima is the maximum field one can have or maximum power one can have from launching a wave in nonlinear medium. I want to find out the second harmonic wave, and the second harmonic wave will be maximized on the condition that delta k tends to 0. That is the condition, very important condition to excel this quantity. So, delta k tends to 0 means what? So, in the right hand side basically we show the condition under which we have delta k equal to 0. As I mentioned, this is a phase matching condition. So, delta k equal to 0 is essentially k2 is equal to 2 k1. K2 is equal to 2 k1 means k2 is 2 omega divided by c multiplied by n2, which is equal to k1 means it will be 2 of multiplied by omega n1 c, because we know in general k is omega divided by c multiplied by n, or in general k of omega is omega divided by c n of omega. So, now if k is 2 omega, we will have 2 omega here and n of 2 omega, which is n2. So, eventually we will have one expression which suggests that it can be possible if the refractive index of 2 omega is equal to the refractive index of omega. So, this is the condition, this is a very critical condition, and normally we do not have this condition because of the dispersion property. So, we will discuss it later, but at this point you should know that if I achieve somehow, if we achieve somehow this condition, we can maximize the power conversion. So, the second harmonic power will be converted more efficiently under this condition. So, the next thing is to find out what is the efficiency. Efficiency is nothing but the ratio of the two powers. So, Pz is the generated power at second harmonic and P1 is the launched power or pump power. So, the ratio between these two is called the efficiency. If I calculate the efficiency from the previous calculation, we will find that again efficiency is a function of the power, and this power is the power of the fundamental wave or the pump. So, it is proportional to pump power and this quantity, this sink value, and again it will be maximized, the efficiency is maximized if P2 is maximized, and this condition is already derived in the previous case, and we will have some relationship here. The most important thing is that this quantity will be maximized, and if this is maximized it will be proportional to z square, which is very important under delta k equal to 0, because if delta k equal to 0 then only we will have this quantity proportional to z square. So, now if I plot, which is very important, this plot is very important, then we will find that we are having a improvement of efficiency, and this efficiency is improving with a function of z square. This is a function of z square, which is improving very rapidly. So, that means I am able to generate the second harmonic very rapidly with respect to z, because it is improving in the form of z square under delta k equal to 0 condition. However, when delta k is not equal to 0, the thing will be proportional to sine square of x. Please note that if delta k is not equal to 0, then this condition will never be 1, and if this is not 1, we will have this as delta k z divided by 2. So, it is proportional to this quantity or the sine square. So, we will have sine square means we will have a sinusoidal variation. So, in the initial few point the efficiency will increase, but after that it will go down to 0 value and then again go to increase and go to peak and go down to some value and peak, and that means the efficiency is periodically changing with respect to z if delta k is not equal to 0. So, this is the interesting thing you should remember, that when delta k is achieved, we have a efficiency is increasing like anything. So, it is proportional to z square, but on the other hand if delta k is not equal to 0, the efficiency is not that much, it is getting some maxima and then go down and so on. So, what is the reason behind that we need to find out. So, now we need to find out what is the coherence length. So, the expression of this efficiency we have already derived, and we find that this is proportional to the sine square when delta k is not equal to 0. So, we find that there is a specific distance of k for which I will have the maximum value, and these maxima will occur when delta k z by 2 become pi by 2, because we know that delta k z by 2 pi by 2 means we will have sine square pi by 2, which is 1. So, this value will reach a maxima when we have this value. So, that means z has to be equal to pi by delta k. So, that is the point which is indicated here, and at that point what happened, we have a maxima. On the other hand, we will have a minima exactly twice of that length. So, this particular length is called the coherence length, which is pi divided by delta k. Delta k can be defined in this way, because delta k is k2 minus 2 k1, and if I simplify that, it should be 2 c omega into n1. So, let me do that. So, delta k is equal to k2 minus 2 k1. K2 is how much? It is 2 of omega of c n of 2 minus 2 of omega by c n of 1. So, if I take 2 omega c common, then we will have n2 minus n1, which is nothing but delta k. So, we just put this term here. So, when we put this term and then simplify this, it will be pi c divided by omega n2 minus n1. So, coherence length is important. Once we have the knowledge of N2 and N1 of a system, then we can able to find out what is the coherence length, because at coherence length we have the maximum efficiency. But after the coherence length, what happened, the efficiency will drop very rapidly and eventually we will not going to have anything at some point. So, here the efficiencies go down to 0. So, you should be very careful under the condition delta k. So, delta k is a condition for which we have some efficiency and we will not going to have anything when we have the distance 2 pi delta k. So, why these things are there, it is an important thing, and we will going to discuss this thing here already, that what is going on. So, we have the wave here, there are two waves. So, once we have the electric field E, so this electric field is nothing but the second harmonic field. Also, we have polarization term which is P nonlinear 2 omega, and which we also have in our hand. The condition, the phase matching condition is delta k equal to 0. So, delta k is equal to 0, this phase matching condition, if I want to figure out in a different way, then we can find one important thing. So, what is the velocity of E 2 omega? From this plane wave expression, we can readily say that the velocity of this E 2 omega is nothing but 2 omega divided by k 2. So, this is the velocity, the phase velocity of the wave to E 2 omega. So, E 2 omega is also moving inside the medium, and P nonlinear 2 omega, which is the source term of this, basically these basically generate this at the same frequency. So, the point is P nonlinear is also moving, this is a moving wave, some sort of moving wave, because we have this plane wave structure. So, it is moving. So, the question is what is the velocity of this and what is the velocity of this. So, we have already calculated that. So, this velocity and this velocity, if I calculate, we have it is 2 omega by k 2 and it is omega by k 1. Very easily one can see that this is the velocity is 2 of omega divided by 2 of k 1, or it is simply omega by k 1. This is the velocity of the nonlinear wave. Now, if I equate these two waves, the phase velocity if I equate, so what essentially we have, omega by k 1 is equal to 2 of omega by k 2, or finally we have k 2 is equal to 2 k 1. It is a very important outcome, and this outcome suggests that the phase matching is eventually suggest that the two waves, the electric field having frequency 2 omega component, which is a moving wave, and the nonlinear polarization, which is also having a 2 omega component, these two are moving in the same velocity. So, when these two are moving in the same velocity, we will have a maximum energy transfer from here to here. So, maximum energy can be transformed under the condition that when the nonlinear polarization of the frequency 2 omega is moving with the same velocity, same phase velocity with the velocity of E 2. Well, we will not going to see much about this. So, today we will going to conclude here, and in the next class basically we try to understand that what is the meaning of phase match in terms of other quantities, that why so that is why actually I try to show this figure. In the next class we try to understand that here we find that the efficiency is going to a maxima and then go down to 0. Why these things is going down to 0 at this from here to here in this length, we try to find out in terms of the phase term. So, well, we will like to conclude here. So, today we will learn a very important thing, that we have some kind of expression which gives us the value of the second harmonic. So, this second harmonic wave, the evolution of the second harmonic wave we derive, and we eventually solve that under the condition that there is pump depletion. So, we solve these things, that there is no pump depletion. That means, if I launch a very strong E1 wave, this E1 wave basically not going to change, and if I take it as a constant, we find that there is no change at all in E1, and as a result we will have evolution of E2 proportional to z square. That means, it is evaluating with respect to z square, and if delta k is equal to not equal to 0, then we find that it is periodically changing. The evolution of efficiency is changing periodically. So, we try to understand the physics of these things. So, in the next class we will start from here and try to find out how the phase is related to this phase matching condition, and how from 2 omega to 2 omega generation is there, and also from 2 omega to omega generation is there, and that is why we will find there is sudden drop in the efficiency. So, with this note, let me conclude here. Thank you very much for your attention. So, see you in the next class.